In this video, we're going to explain how expanded valence shells form and why they cannot form below a certain energy level. The first example of a compound with an expanded valence shell that we'll look at is PCl5. If we examine phosphorus's orbital energy diagram, we see that it corresponds exactly with phosphorus's Lewis structure. This lone pair is represented by the pair of electrons in phosphorus's 3s subshell, and each of the 3 unpaired electrons corresponds with the 3 unpaired electrons in phosphorus's 3p subshell. The problem is that in order to make 5 bonds, as it has in PCl5, phosphorus needs 5 unpaired electrons. Now, if we do the same thing as in sp3 hybridization, if we take this paired electron from the 3s subshell and jump it to a higher energy level, we can get 5 unpaired electrons. But where exactly does it go? Well, if we think about what happens at energy level 3 is the first time where we start encountering d subshells. So if we were to take one of the electrons that exists in phosphorus's 3s subshell and jump it up to the 3d subshell like this, we can end up with the 5 unpaired electrons that are needed in order for phosphorus to form 5 bonds. The problem is that, again, just like in sp3 hybridization, doing this violates the Aufbau principle, because in order to fill the 3d subshell, we not only need to fill the 3s and 3p subshells, we actually need to fill the 4s subshell before we can start adding electrons to the 3d subshell. So how can we get around this without violating the Aufbau principle? The solution, as some of you might have anticipated, is to take all of these orbitals together and form a new hybrid subshell that allows all of these electrons to enter orbitals because they are all at the same energy level. So by doing this, we're taking the orbital that exists in phosphorus's 3s subshell, all 3 orbitals that exist in its 3p subshell, and one orbital from the 3d subshell, hybridize them together such that we get one subshell that has 5 orbitals where every electron can exist by itself as an unpaired electron in the same subshell without violating the Aufbau principle. And if we count which orbitals we hybridized, we're at energy level 3, and we hybridized one s orbital, 3p orbitals, and a d orbital, which means that these new hybrid orbitals are what we call sp3 d orbitals that again allow phosphorus to effectively have 5 unpaired valence electrons, thereby allowing it to make 5 bonds. For the people that are wondering, well, why can't nitrogen do this as well? Well, again, this is why energy level 3 is special. Let's say that nitrogen wanted to do this. If we wanted to jump nitrogen's paired electron up to a d subshell, well, then it would be added to nitrogen's 2d subshell. Now, the problem with that is there is no 2d subshell. It does not exist, because the first time we start seeing d subshells is at energy level 3. And for that reason, nitrogen is impossible to end up with 5 unpaired electrons, because there is nowhere that its paired electron can jump to, and for that reason, we can only start seeing expanded valence shells at energy level 3. If we take a look at a second exemplar compound, that compound is sulfur hexafluoride, which is again sulfur bonded to 6 fluorine atoms. If we take a look at sulfur's orbital energy diagram, just like with phosphorus, we see it matches up with its Lewis structure, where each of the lone pairs corresponds to a pair of electrons, the first of which being in sulfur's 3s subshell, and the second of which in the first orbital of its 3p subshell. Now, if we wanted to make 6 bonds, we would need 6 unpaired electrons, which means we would need to take these 2 paired electrons in phosphorus's 3s subshell and in its 3p subshell and jump them up to a higher energy level. And where would they go? Well, we already know the answer from phosphorus, because at energy level 3, this is the first time where we see the 3d subshell. So these 2 electrons can jump up to the 3d subshell, and if we write in all of our electrons, we now see that we have 6 unpaired electrons, allowing sulfur to make 6 bonds. But again, we have the same problem. We cannot fill the 3d subshell with electrons until both the 3p and the 3s subshells are completely full, because this violates the Aufbau principle, which is why we undergo a hybridization event. We're going to take sulfur's 3s subshell, all 3 of its 3p orbitals, and 2 orbitals within its 3d subshell, and hybridize them together such that we get a new hybrid subshell involving these 6 orbitals here. And if we count which orbitals we hybridized, we took 1 from 3s, 3 orbitals from 3p, and now 2 orbitals from sulfur's 3d subshell in order to make this hybrid energy level, or rather hybrid subshell. And because these are what we combined, this hybrid subshell, or these hybrid orbitals, are what we call sp3d2 hybrid orbitals. And because all of these orbitals exist at the same energy level, we can now fill each orbital with 1 unpaired electron, effectively meaning that sulfur now has 6 unpaired electrons, allowing it to make up to 6 bonds. And with that, that concludes our examination of relating orbital energy diagrams with Lewis structures, and explains why only certain elements can form an expanded valence shell as long as they are above energy level 3, because that is the energy level at which electrons can jump up to a d subshell.